Check this out. I'm just gonna drag this plate through the water in the pool. That's it, but look what forms.
Perfect black circles on the bottom of the pool. And it's so weird, they don't die. They just keep going right next to each other. I sped this footage up because the circles took 3 minutes to cross the pool and didn't seem to be dying out. These got sharper as they went and made it all the way across.
So cool. And look closer, you can see what's causing them. There are 2 almost unnoticeable dips in the surface of the water. Why don't they die out? And how do these dark spots form? And why do the dips move together? So many questions. Let's first look at what they are. When I dragged the plate through the water, you could see it forming little vortices like you get when you move a paddle through the water. A vortex is a gas or liquid moving in circles with what we call a vortex line going up through the circles. They are everywhere. Tornadoes, water flowing down the drain, hurricanes, or the movement of air over an airplane wing. Vortices often form when there's a difference in fluid speed, like fast wind moving over slow wind. As you move the plate forward, the water right next to the boundary moves with the plate because of friction. The water further out is not moving. It's that difference in velocity that causes a shear force and starts the water spinning. This is accentuated by the water in front of the plate being forced around the sides and the water behind the plate being sucked forward as the plate moves along. In this coherent vortex, our dips can travel much further across the pool than a ripple without dissipating. Why? The vortex wants to keep its angular momentum, so it continues spinning as it moves through the water and only loses some energy through friction to the surrounding stationary water. So what we appear to have here is 2 vortices moving across the pool, but it seems weird that they stay right together. Well, when we create this vortex, we're forcing water to move around the whole plate, not just on the surface of the water. Our vortex line is curved. We're creating a half vortex ring. You know, like a smoke ring, bubble ring, or even the plume rising up from an explosion, but half of that. These 2 dips on the water's surface are just the ends of the half ring. They're connected, and that's why they stay together. We can see this if we put a little food coloring into the ends.
The food coloring travels from one end to the other and you can see the entire half ring.
So cool! We just made a bubble ring without the bubble. This also tells you something interesting. The half ring is not a wave.
From one end to the other and you can see the entire half ring.
So cool! We just made a bubble ring without the bubble. This also tells you something interesting. The half ring is not a wave. A wave is a disturbance moving through a medium that transfers energy but doesn't transfer matter. When we added food coloring, we saw clearly that the vortex is transferring matter just like a smoke ring does. So sadly, it's not a wave. It's cooler than a wave. Now back to this half ring vortex. Isn't it weird? You've probably never seen half of a smoke ring before. Why? Well, according to Helmholtz law, a vortex line cannot start or end in a fluid. So a vortex line either wants to close into a loop or end at a boundary. If you tried to cut a smoke ring in half, it would either break up or, even cooler, it would break up into 2 smaller smoke rings.
I don't know if that happens. It would be awesome.
Since the line can't end in the fluid, it ends at the surface. You almost never see these half vortices though because they have to occur on the boundary of 2 media. If you can think of another way to make the entire half ring visible, like a smoke ring or a bubble ring, let me know. So now, why does our vortex create those cool dark spots?
Well, the balance between gravity, centripetal forces, and surface tension creates a funnel shape which acts like a lens.
Lenses often work by focusing light to a point, like this Fresnel lens, which can melt pennies in the sun, but I digress. Our vortex lenses
and surface tension creates a funnel shape which acts like a lens.
Lenses often work by focusing light to a point, like this Fresnel lens, which can melt pennies in the sun, but I digress. Our vortex lenses focus the sunlight away from the center, like so, and you have a bright ring surrounding a dark circle. The ring highlights the dark circle further, and you get these incredibly clear black spots. So cool! Now I highly recommend trying this at home, especially if it's too cold to swim in the pool. Here are some tips. The water has to be very still. Even a small breeze makes it harder to create these. The sun has to be out or it won't work. And you can try some other really cool things. Send your vortices at a wall. You'll see the dark spots spread out. Or try colliding 2 of them. Happy physicsing! Hi, I'm Diana, and you're watching Physics Girl. So, I grew up in Hawaii. This episode is sponsored by Audible. Welcome to the science. Have you seen this experiment before? With the milk and the food coloring? And then you put some dish soap on the end of a Q-tip and you dip it in the middle of the liquid to get this awesome experiment. This is the kind of experiment that never gets old. But if you're like me and you fidget a lot and you keep playing with it, you'll notice that if you flick the Q-tip across the surface of the water, you get these little beads that roll across. They're like little bowling balls that roll across. Oh my God, that's so pretty. I have to take a picture. Blah. Thanks to some phantom high-speed footage from Beyond Slow Motion, awesome channel, definitely check it out, link is in the description. You can see that these beads form as streams of milk break up into individual droplets and then bounce on the surface. It's so mesmerizing. But what are they? I drove myself crazy, Googling every different combination of soap and milk and food coloring and liquid, and I could not figure out what they are. So I did what I always do when I need to know something. And I asked my physics friend Dan Walsh, who immediately said,
Anti-bubbles.
I thought he was joking.
You think I'm joking?
Turns out, he was close. Anti-bubbles are even cooler than this. Dan, are you ready for this?
I was born ready.
Oh yeah! That's amazing! I am here with Ashley, who's my intern, and Dan, who's my friend and is just really enthusiastic about physics. Also a PhD student in physics.
That's another reason why I'm so interested.
Yeah. Also a student of physics. So much physics here. So anti-bubble is the exotic sounding name given to these little spheres that we've made underwater because they're kind of like the opposite of a regular bubble. A regular bubble is a thin film of a liquid enclosing a gas and then typically floating in a gas like air, whereas an anti-bubble is a thin film of gas enclosing a sphere of liquid and then typically fully submerged in a liquid. Do you want to try this one? Oh yeah.
Just try a bunch of different parameters.
So you've got to put water in both of these containers, then add soap, mix it all in, and then you squeeze water from this container onto the surface of this one. Oh, that was a good one.
But
it's easy to see the structure of the anti-bubbles when we added food coloring into the squeeze bottle, because then when they pop, you can see that colored liquid come out, typically making the shape of a vortex ring. Oh, that's so hard.
Did you see how there was a little regular bubble that came up?
By using high-speed cameras, physicists have observed that the air at the bottom of the anti-bubble floats to the top, popping the air film. You've now got a little air droplet that floats to the surface, which is just the opposite of a popped bubble, where the liquid film falls because of gravity. Thank you guys.
Sure, thank
High
you.
So despite sounding like some exotic form of matter, anti-bubbles are actually just as common as regular bubbles. You make them when you wash your hands with soapy water, but they pop much more easily than regular bubbles. Why? Wait, so why do regular bubbles pop? So you form a regular bubble by decreasing the surface tension of water. And when you decrease the surface tension, bubbles can live a lot longer. There's actually a really interesting molecular reason why bubbles keep their nice spherical shape. It works like this. Each soap molecule has a hydrophilic, that is a water-attracting head, and a hydrophobic, or a water-repelling tail. When you make a soap bubble, the soap molecules line up so that hydrophobic heads are in contact with the water. They have a slight electric charge, which means that the soap molecules on one surface of the film repel the soap molecules on the other surface, which helps keep the film from collapsing in on itself. That is, until the film evaporates. Now, an anti-bubble, on the other hand, is also made of soapy water, but there are a few key differences. Everything's all flipped around. So the anti-bubble air film, the hydrophobic tails are now facing each other in the film, and the hydrophilic heads are facing away in the liquid. Soapy water is actually a good electrical conductor, which means that electric charges can flow easily through it. So those slightly charged hydrophilic heads attract oppositely charged molecules in the water, basically neutralizing the charge at the surface of the anti-bubble air film. Those electric repulsive forces that basically help the bubble keep its shape don't exist in anti-bubbles, and so they pop much more easily than their regular bubble cousins. No! So as you can see, they're kind of hard to make. Like, we struggled with a lot of the steps. Don't put too much food coloring.
Yeah.
I would suggest practicing without food coloring first, because otherwise you're going to make all the fluid red.
Yeah. The other trick is that if you add some corn syrup into this bottle, you'll increase the density of this liquid because corn syrup is more dense than water, so that you can get your antibubbles to sink. Or even get a little bit of the corn syrup in here mixed in the bottom so that you've got a gradient of density from more dense to less dense. Then when you squeeze this liquid into the cup, you could get them to float right in the middle, kind of like a neutral buoyancy in that level of the liquid density. It takes a lot of patience. They're so cool! Ah! I love science. So if you were to make an anti-bubble in space where there's no buoyant forces caused by gravity, you could make the anti-bubble last a lot longer. Destin over at Smarter Every Day is making a video with more about this, so as soon as that's up, I'll put the link in the description. Even after all this explanation, there's still a lot we don't really understand about anti-bubbles. So stay tuned for the research on this and potential applications. There are 10 types of clouds. Fluffy, swooshy, I kid. But really, there are 10 types of clouds. And beyond that, people have categorized them into subvarieties. Capillatus, mammatus, lenticular, fall streak, cirrus vertebratus, cumulus congestus, pyrocumulus, stratiformis, altocumulus. But today, people have categorized them into